Hello, I am Dr. Jason Mast, and in this lecture I will cover the fundamentals of significant figures. First, let me tell you the goal of using significant figures. Scientists perform experiments and make measurements. With those measurements, computations are done. So, for example, the distance an object travels and the time it takes can be divided to compute the average speed. Here, the distance traveled and the time taken are measurements, and the average speed is a computation that is done with those measurements. The measurements that were made have limited precision. So, for example, rulers can only measure to the nearest millimeter, and most stopwatches measure to the nearest centisecond, that is, 1/100th of a second. The question becomes, what is the precision of the resultant computations? The method of significant figures is one method of addressing this question. Significant figures keeps everyone honest about the precision of their measurements and the results. The problem is that displaying too many figures is dishonest. Let me show you. For example, 123 meters was traveled in 53 seconds. The average speed is 123 meters divided by 53 seconds, and we get approximately 2.320754, and then there's more digits, in meters per second. The result here claims to have 19 significant figures. However, in all of civilization, there does not exist any instrument that can measure that many digits. This result is dishonest about its precision because the result cannot be more precise than its inputs. And so we will look at significant figures as a way of keeping us honest about the precision of our results. Let's do an example of addition. Let's say you wanted to add two length measurements, 1.3 centimeters and 0.28 centimeters. What is the resultant sum? First, you would write out the problem like this. First, you would convert both quantities to the same unit, and in this case, they're already both in centimeters. And then you would line up the two numbers at the decimal point. The resultant sum will be in centimeters because both inputs are already in centimeters. And now we add the digits going right to left. Above the 8, no digit is written, so we just assume that it's 0, and I'll put it in here in red. And so 0 plus 8 is 8, 3 plus 2 is 5, and carry the decimal point, and then 1 plus 0 is 1. And so the calculator will tell you that 1.3 plus 0.28 is equal to 1.58. However, the digit 0 may not actually be 0. The person who did this measurement did not write down 0. They didn't write anything. Because they didn't write anything, that means that it is unknown. It is not measured. We don't know actually what it is. It could be 0, but it could be any other value. And so in reality, it's not 0, it's a question mark. It's a variable. And so the more honest addition is, what is an unknown value plus 8? Well, that's just a different unknown value. That is at least 8. It could be larger. Again, the reason we say that the digit is unknown is because it wasn't measured. Digits that are measured are written down, even if they're 0. Digits that are not written down were not measured, and that's why they weren't written. And that's the lesson here. The values 1.3 centimeters and 1.30 centimeters represent different levels of precision. The length 1.3 centimeters was measured to the nearest millimeter, whereas 1.30 centimeters was measured to the nearest tenth of a millimeter. And so the correct answer is 1.6 centimeters. The reason the 5 became a 6 is because the digit after that is at least 8, or it could be larger. And so when rounding, the 5 will become 8. And so 1.3 centimeters plus 0.28 centimeters equals 1.6 centimeters. Let's now look at scientific notation. Any quantity n can be written in scientific notation, and it looks like this. N equals a times 10 to the power of p and has some unit. Here a is a number between 1 and 10 and includes trailing zeros that happen to be significant, and p is an integer that is the exponent. Here are some examples. 4,568.300 seconds can be written in scientific notation like this: 4.568,300 times 10 to the power of 3 seconds. This quantity has 7 significant figures, and the 2 trailing zeros are significant, and so they are included when writing it down. Here's another example. 0.0018220 meters can be written as 1.8220 times 10 to the power of negative 3 meters. Here again, the trailing zero is significant, and so it is included. In both of these cases, the number 4.568,300 and 1.8220 are A, and the exponents are 3 and negative 3 respectively. Be sure to pause here and review this to make sure that you understand how any number can be written in scientific notation. On this slide are various examples of quantities with 1, 2, or 3 significant figures. Pause here to review these quantities and make sure you can identify which digits are significant and which digit is the least significant digit. It is important to note that a zero may or may not be significant depending on its placement. To help clarify which zeros are significant, quantities are often written in scientific notation. If you are unsure about any of these, reach out to your instructor for clarification. Let's now review the rules around significant figures and mathematical operations. For addition and subtraction, the least significant figure in the result is limited by the least significant figure of the inputs. For multiplication, division, powers, and roots, the number of significant figures in the result is the minimum number of significant figures of the inputs. The above rules only apply to the final result. Keep more digits for intermediate computations and round in the end. We'll see some examples of these on the next slide. But also note, significant figures only apply to measurements. Exact quantities, such as definitions, integers, and unit conversions, generally have unlimited precision. Let's now do some examples. Let's say, for example, we would like to compute 55.658 plus 2.41 minus 0.0550. If you type this onto a calculator, you will get 58.013. Now we need to identify which digits are significant. In the first term, there are 3 digits that are significant past the decimal point. In the second term, there are 2 digits that are significant past the decimal point. And in the third term, there are 4 digits that are significant past the decimal point. The limiting term is the second one, which only has 2 digits that are significant past the decimal point, which means that in the final result, there can only be 2 digits past the decimal point that are significant, and so we drop the 3. And the final result is 58.01. Now that was for addition and subtraction. It's a little bit different for multiplication and division. Let's say you would like to multiply 5.04 times 18.33 times 2.000. If you multiply this on a calculator, you will get 184.7664. Now we need to identify which digits are significant. The first factor has 3 significant digits, the second factor has 4, and the third factor also has 4. 3 is the lowest number of those 3, and so the result can only have 3 significant figures. The 4.7 will get rounded up to a 5, and so the final answer is 185. In this next example, we'll take the square root of 1.2 divided by 0.0703. If you type this onto a calculator, you will get a very long number, 4.131549, and then many more digits. We need to truncate this number to the correct number of significant digits. In the numerator of this ratio, there are 2 significant figures. In the denominator, there are 3. 703 are significant. Here we are dividing, and so our result is limited to the minimum of 2 and 3, which is 2. And then the square root will also have the same number, and so that means the final result can only have 2 significant figures. And so the result is 4.1. Go ahead, pause here, and review these examples, and make sure that you understand how the correct number of significant figures was determined. If you have any questions, please reach out to your instructor.